Hi, it's time for another math easy solution to discuss further into conic sections and now look at hyperbolas and go over the definition and derivation. So let's go ahead and jump right in. So first of all, I want to make a note. I had made a previous video actually several years ago on the definition of hyperbolas, but I'm revisiting it to better tie it to the conic section series that I am making, and also just to provide a better or more detailed video on the definition. Yeah, so now recall from my earlier videos which I went over the ellipses and the parabolas. So basically recall that parabolas, ellipses, and also hyperbolas are called conic sections because they result from intersecting a cone with a plane as shown below. Yeah, so here we have ellipse, there's parabola, and there's hyperbola. And the ellipse is if you cut it on one of the cones perfectly across like that, then you get this circle or ellipse. If it's a circle if it's flat. And then the hyperbola is you go against on one side of this, of one of the cones, and then hyperbola is if you get a plane that cuts through both of the top and bottom as this vertical one over there. So essentially you get basically two parabolas in this hyperbola. So very, very interesting stuff. So let's go further. So hyperbolas. A hyperbola is the set of all points in a plane, the difference of whose distances from two fixed points f1 and f2, known as the foci, is a constant. So this difference is a constant. And that is the definition of hyperbolas, and I'll illustrate that right now. So this definition is illustrated below. So if we have, let's go like this. This is the y-axis, and this is the x-axis across here, x and y. And let's say here's the origins at 0, and let's say we had a foci here and here, two fixed points. I'll call this one f1. I'll just move this over. Let's say this is our foci 1, f1, or focus 1, or the first focus, and this is going to be at 0. Actually, let's say not 0. It's at a distance of negative c and 0, and then this distance from here to here, the coordinates of the second one, let's say it's also c and then 0 there. So 0 for the y-axis, x-axis, it's a c across there. Now let's say we have a point across here, and this point, and I'll call this p of x, y, and now what I'll do here is draw this in red, the distance from this one to this line across, or to that point. So this is going to be our distance here. Yeah, so this distance all the way in red, and I'll call this a distance p f1, like that, absolute value, just a distance. Put these lines across there. Alright, and now the distance from here to here is going to be, well, p and then f2, absolute value. That's the distance from there to there. Now if the difference between these two distances, so the difference of whose distances from two fixed points f1 and f2, so the difference between these ones, if they're constant, then this is a hyperbola, and the shape will look like that. All the points that can be will look something like this, because as it goes more to the left, this one's going to get smaller. When this one gets smaller, this has to get smaller as well, because the difference needs to be constant until it gets to a point like that, and also curves back out, basically a horizontal parabola across this and there. It's going to look something like this and keeps going on. And likewise from this side as well, if you just mirror it across, it's going to go like that. And that's how it's going to look like. And basically we could write, well, p of x, this right there. Yeah, if we just make it more general, so p of x, y as basically, again, the set of all points on this on these curves. So p of x, y is a hyperbola. Hyperbola if or instead let's write when. So it is when, by definition, the difference between these two are constants. In other words, p of f1, the difference minus p f2 equals to constant. And likewise as well, if you have the other one subtracted by the other one, you'll also get a constant. It'll just be switching signs from minus or positive. So yeah, I'll just circle this. So basically that is a definition of a hyperbola. And now I'll briefly cover just some interesting facts about hyperbolas. So hyperbolas occur frequently as graphs of equations in chemistry, physics, biology, and economics. as in Boyle's law, Ohm's law, and supply and demand curves. And a particularly significant applications of hyperbolas is found in the navigation systems developed in World Wars I and II, which I may cover in a later example video, so stay tuned. Yeah, interesting stuff there. And also notice that the definition of a hyperbola is similar to that of an ellipse, which I covered in my earlier videos. Put that in the link in the description below. The only change is that the sum of the distance has become a difference. So the other one, instead of a difference, we had it a plus for an ellipse. So ellipse has plus, this one is just minus. So yeah, very cool stuff. So in fact, the derivation of the equation of a hyperbola is also similar to the one given earlier for an ellipse in my earlier video. So even the derivation all very similar. So make sure to watch that video. Yeah, so now let's look at the derivation. So let's derive the formula of a hyperbola when the foci are on the x-axis at plus or minus c and 0 there. So it's on the x-axis, the y-axis is basically 0 there. And the differences of the distances is pf1 minus pf2 equals plus or minus 2a, and I'll explain why there we have this one. So basically note the constant plus or minus 2a can be seen as the vertices of the hyperbola, in other words plus or minus a and 0, because the distance between the vertices is plus or minus 2a depending on which distance we subtract from the other. In other words, these points right there, that's going to be at plus or minus a and 0 there, and I'll explain that right now. Yeah, so if we draw the hyperbola again like this, it's going to look something like this, and this is our foci. I'll call this f2, and this is going to be our f2, and it's going to be at c, or positive c and 0. The f1 is going to be somewhere across here, and this is going to be at negative c and 0. And now the vertices, that's going to be at here. This is at point negative. This can be negative a and 0. And then we have all the way here. I'm just going to put an arrow actually instead. Yeah, I'll put an arrow because this is going to have how the shape's going to look like something like this. And then at this vertice right here, this is going to be negative a and 0. So then this distance from here to here is just going to be a. And then from this point right here is the other vertice on this side. It's going to look something again like that. And then this is going to be positive a and 0. And this distance again is from here to there is going to be a as well. And then let's say we have a point here on the parabola. This is going to be our point P, just a general one, P, X, Y, like that, the coordinates. Yeah, so thus the distance from here to here, this is again going to be our, we'll call this distance across P, F1, absolute value, just a distance. And then this one right here is going to be P, F2. Yeah, here I quickly just moved the foci, just separated more, just be easier for the derivation as I'll continue in this video, just to make this like a triangle there. Yeah, so now as shown above, if the definition is that the difference has to be constant from these two distances, as this one goes closer and closer to here, this distance is going to be, or have to be 2a, and I'll just show you that right here. Yeah, so what we have is thus the absolute, the differences, let's go pf1 minus pf2. Yeah, this equals to constant. If it equals to constant for any value of this p, it's still going to be constant. So let's say at, or I'll just write when, p of xy is equal to, or it's at the point right here at a0, and I'll just write p of a0 like that. So it's at the vertice. Yeah, then what we end up having is, and I'll write then, the difference p of f1, this is going to be from here to all the way across there. And this distance is, yeah, this isn't going to be, actually I'll draw it better like this. I'll draw a straight line like this. So this is our f1. It's going to be at, I'll just write the f1 like that. Then we have the origin. I'll draw a straight line like this on the x-axis, because it's all going to be on the x-axis when this is at the bottom there. If this is right here, our 0, then what we have here is our f2 like that, and then this is the point P. I'll draw it better actually. This is our point P across here, and this is at a 0. So then this distance is A, and also this distance from here to here is also going to be our A there, like this, and this is our negative A 0. And then distance from here to here, I'll just call this J. And it's all symmetric, so this is also going to be J from here to here as well. So this means now the distance is, so P of F, move that over there, so this is going to be our P, A is 0. So then distance, this one from there's going to be equal to 2A plus this J. And then likewise, what we have is, and P of F2, so from here to here, that's just going to be our, this just equals to J, like that. So then what we end up having is the absolute value P of F1 is P of F1 minus, or the difference P of F2 is equal to 2A plus J minus the J. So the J cancels. This equals to 2A. Or we could do, or switch it the other way around, and we have P of F2 minus P of F1. So then what we end up having in this case is a P of F2 is going to be J minus 2A plus J, like that. So then we get a negative 2A equals to negative 2A. So then hence what we get is our plus or minus 2A, and our constant right here is going to be plus or minus 2A, and that is why it's chosen as this over there. I just wanted to cover that quickly. Alright, so now that that's covered, let's look at it more generally when it's not on the x-axis. So now, or I'll just write more generally, or in general, let's write in general is better. In general. So yeah, in general, what we'll have to do is use the Pythagorean theorem right here. Yeah, so in general, what we're going to have to do is, if it's not on there, we're going to have a triangle like this, and what I'm going to do now is draw this down in blue, like this, so just a perpendicular line across, so then we have distance from here to here is just going to be y, so y, and then the bottom part is 0, so y all the way to the x-axis, and then the difference between here and here, so I'll draw it like this distance is going to be, it's going to be, well, c, and then this is going to be all the way to the x point. So I'll just say the absolute value of the difference, x minus c. So just x minus c, just look at the absolute value, or the difference between x and c. And yeah, now let's look at the difference all the way across here. So from the f1 all the way to this point, what we end up having is, well, first of all, from here to here is going to be just 0. So from, it's going to be c. So from here to here is c, like that, is c. And then from here all the way to across there is going to be, across this one like that, that's going to be x, like that. So then distance from here to here all the way to across this part is going to be like this, all the way across to here is, this is just going to be, well, x plus c. Let's write this down as x plus c. Yeah, so now that we have this, we could just apply Pythagoras, because we know the y here, we know the horizontal distance and the vertical. We can get the slant lines like this, the PF1 and also the PF2. So let's go here. In general, and using, so I'll write in general and using Pythagoras. Let's write and using Pythagoras. Actually, that's spelled wrong, it's just AS like that. So in using Pythagoras, the difference is now, or first of all, just write this down, the definition, PF1 minus PF2 equals to plus or minus 2a. And again, it could be plus or minus because it depends on which one you choose, PF1. It could be the left side or the right side and where the point is, and so on. But it can be constant, plus or minus 2a. So now the PF1 is going to be this line across here. So using Pythagoras, x plus c squared plus y squared equals to this one. So in other words, we could just square root that one, and we want the positive side, so it's absolute value. So what we get is square root, I'll just put this in here, x plus c squared actually no, it's just squared around it. So x plus c, that's the horizontal one, squared plus the vertical one, y squared, on the side of the triangle, and then we just square root all of it, and we're only going to take the positive because it's absolute value. So that's a distance, and then subtracted by, then we have on this side this triangle PF2, so x minus c squared, absolute value is going to be squared like that, doesn't matter, and then plus the y squared to get to that one squared, and then square root it. So we get a x minus c squared plus a y squared, and then like that. And yeah, just for completeness, I had the absolute value there. We keep it there, we could remove it, doesn't matter, because when you have an absolute value and squared, it's always going to be positive anyways. And this equals to plus or minus 2a, like that. Yes, so now what I want to do is get rid of these square roots. What I'm going to do is move this whole term onto this side. Yeah, move it all the way across there, and then square both sides. So that's minus, move it over there. So then, and then this becomes just brackets normally. So here we get an x plus c squared plus a y squared equals to plus or minus 2a, like that, 2a, and then plus this giant square root, x minus c squared plus y squared, like that. And now time for some squaring of both sides. So we have squaring on both sides. So we're not changing anything, we're doing both sides, so we get rid of this square root on this left side, and we can also get some cancellations on the right side, and see, just to simplify it further. So this just becomes, well, x plus c squared plus y squared. And now we could just expand this on the right side, and so then this one multiplied by itself is going to be, this is going to be, well, 4a squared. So basically the plus or minus disappears, because if it's minus, then it's minus squared is going to be positive. Minus times minus is going to be always positive. Negative times negative positive. If it's positive, squaring it's just going to be positive times positive. So it's still going to be positive. So then we do that, and then this part multiplied by this side is going to be plus or minus 2a, and then square root x minus c squared plus y squared, like that. And now if we continue to FOIL it out, now this side, what we'll do is multiply it by this one here, and that's going to be another plus or minus 2a, so I'll just replace this to make it easier, or just quicker. So that's just 4a. If you don't know why I did that, go read up on my earlier videos. Just basically basic foiling or expanding that. Now this one multiplied by itself is going to be plus, and then we have x minus c squared plus y squared. And now we can cancel, well, one of the terms, this one right here and this y squared. Those can cancel, so we can cancel those out, and now the next one we can just expand this and this. So we can expand this, so now we have over here this x times x is x squared, x times c is, well, plus cx, and then c times x, that's another cx, so let's add a 2, we're going to add them up. And then c times itself, c squared, like that. And now this equals to 4a squared plus or minus 4a square root x minus c squared plus y squared, like that. And then likewise here we can expand that. That becomes x times x is going to be x squared. X times c, negative c is going to be negative cx. Negative c times x, it's another negative cx. Put a 2. Negative c times negative c is going to be plus c squared, like that. So we have this. Now let's look at some more cancellations we can do. We can cancel this x squared, this c squared, and this c squared. And now this part here, we can move this over to this side so that they can add up. And then when they add up, we get a 4cx, 2cx plus 2cx. There, 4cx equals to 4a squared, remove all the cancellations, plus or minus 4a square root x minus c squared plus y squared. Yeah, so now that we have this, we can cancel all the 4's out. So all the 4's cancel, and I'm going to do now is move this a onto this side, and then basically do another squaring of both sides. So all the 4's are gone, so now we have a cross here, cx minus a squared equals to a plus or minus a square root x minus c plus a y squared, like that, plus y squared. And now what we do now is we can square both sides, so we can get rid of the square root as well as this plus or minus. So we can square both sides, square both sides. So again, if it's negative, squaring it just becomes positive, because negative times negative is positive. So what we have here is, and here I'll do this all in one go. So this part here on the left side, we have cx times itself, so it's going to be c squared x squared. And then minus, well, I mean, not minus, this times this, yeah, this is going to be minus. This is going to be a squared cx. And then likewise, this multiplied by this side, now we have another negative a squared cx, so that's just going to be 2 there. So just put a 2. And then negative a squared times by itself, that's going to be positive a 4. So yeah, the squares add up to 4 there. And then we have over on this side, this becomes, well, that's positive. The a is going to be, well, a squared. And then the square root gets cancelled. So what we end up having is just this term inside, but let's just expand it to save time. So what we have is now this x minus c squared. So we have x times x is x squared. X times negative c is negative cx. And then negative c times x, that's another negative cx. So we add those up. It just becomes a 2. And then we have negative c times negative c, just by itself. Times negative c is going to be positive c squared. And then we have this y squared over there, like that. Yeah, so then now we have this. Then we just multiply the a inside and cancel some like terms. Let's write this on this side. A squared x squared minus. Now we have a minus this right here. This is going to be 2a squared cx plus c plus a squared there. A squared c squared. Then plus this y squared over there. Yeah, now what we can do is cancel some terms. We can cancel this one and this one, and in fact, yeah, that's only one we can cancel right now. But what we can also do is move the x and y variables. I'll move those all to the left side, all to one side. So there's a y over on this side as well. And then I'm going to move the or just the constants or the variables, non-x or y variables onto this side there, so that we have this with this one. So then what we end up having is this. We get, and also yeah, forgot to add the a here. So forgot to multiply there. There's just a y squared like that. Yes, okay, much better there. A squared y squared. Okay, it's just corrected myself there. So we move this all to this side. We get here is cx squared, and then we have this part here, c squared x squared, and then we have a minus this part, a squared x squared, and we move this over, we get a squared y squared like that. And then on the right side we get this part here, so this goes over to this side. This equals to a squared c squared minus a to the 4. And now what we can do is, well, if we notice this x terms, if we factor out that x term out of there, what we end up getting is I'll just factor this x squared on this left side. And then we have a c squared minus an a squared there. And we could also do that over on this side as well. What I'm going to do is write this as a squared c squared minus, and this is just same thing as writing a squared times a squared. So that if we factor out an a squared, we just get an a squared, a c squared minus a squared, just like this. So we have that part minus this a squared y squared. And then basically move this down over to this side and also factor out the a squared. So we get an a squared out of there. So we get a c squared minus an a squared, bracket closed like that. And now what I'm going to do is let b squared equals to c squared minus a squared. Yeah, I'll just write this a bit better. So a squared like that. So b squared, let that equal to c squared minus a squared, so we could simplify this whole function. So then we end up getting is, yeah, so thus, and I'll just put an arrow here, thus we have is b squared x squared minus a squared y squared equals to a squared b squared like that. Absolutely genius stuff here. And then we can divide both sides by an a squared b squared, and so on, a squared b squared like that. Just divide that out. So what we end up getting is, and then basically when we divide both on this left side, the b squareds cancel, and then this one, the a cancels there. So what we end up getting is a x squared over a squared minus, then a squared cancels there, y squared over b squared, and this all cancels, equals to 1. There's our hyperbola. And I'll just write this down as our hyperbola right there. Hyperbola, like that. So also note now, yeah, if we put x equals to 0 into the equation, what we end up getting is, well, 0 minus a y squared, because 0 squared is 0. Y squared over b squared equals to 1. Just move this over, and then move the negative over. What we end up getting is, is a y squared equals to negative b squared. And when we square both sides, what we end up getting is y equals to a plus or minus of a negative b squared, but then negative times b squared. But this can't be less than 0, so this is always going to be negative unless b itself is 0, but I'm not sure if it can be. So anyways, this is less than 0, so this is not defined, or it's undefined, like that. Yeah, it's undefined. And before I get to the next part, so if b is equal to 0, if you go all the way up to here, and before the division, if you let b equal 0, all we're going to get is, well, this vanishes, we just have a y equals to 0. Which is just nothing. Yeah, which is just the x-axis. So anyways, so thus there is no y-intercept because y squared can't equal to negative b squared. It's impossible unless we deal with imaginary numbers. And also put a note right here. Note if b is equal to 0, then what we end up having is, basically if it's equal to 0, then what we have then. So if it's equal to 0, then we have the x squared over a squared minus, actually no, before we divide it out. So we just get this top part. There we have a b squared x squared minus a squared y squared equals to a squared b squared. So if it's equal to 0, we get a 0 minus y squared a squared equals to 0. In other words, a y equals to 0. Which is just nothing. So yeah, that's just not going to help us out. So it's not a hyperbola, it's just nothing there. So the hyperbola, just bring out more properties of it. The hyperbola is symmetric with respect to both axes or axes, because it doesn't matter if you put positive or negative, i.e. if you put negative x inside the squared, a squared minus a negative 1 on this one. It doesn't matter if you put plus or minus inside for x or y or b squared. This is nonetheless going to be still equal to, well, positive x squared a squared, because the squares always make it positive. Y squared over b squared, then this all just equals 1. And now to analyze further the hyperbola, what we notice is that, well, if we have x squared over a squared minus y squared over b squared equals to 1 right here, and if we move this over to this side, what we end up getting is then what we get is x squared x squared over a squared equals to 1 plus y squared over b squared. Now this part right here is greater than or equal to 0, so it's greater than or equal to 0. Let's put it like that. So this is greater than or equal to 0, so that means that, and if that's greater than or equal to 0, that means this entire thing, so is going to be greater than or equal to 1. So that is just 1 plus a number greater than 0 or equal to it. So it's greater than or equal to 0, so then what we end up having is, move this down here, x squared over a squared is greater than or equal to 1. Now we can move this a squared on this side, so what we end up getting is an x squared is greater than or equal to a squared. And then when we square this out, what we end up having is, well, since we're dealing with inequality there, so x is going to be, the absolute value of x is greater than or equal to the absolute value of a there. Or I mean just greater than a right here. A is assumed to be positive constant there, so it's greater, the absolute value of x is going to be greater than that. In other words, that's the domain of the x of the hyperbola. So thus, absolute value of x greater than or equal to a. This just means that x is going to be greater than or equal to a if x is greater than or equal to 0. But if it's negative, so then this is going to be x is less than or equal to negative a if x is less than 0 for the negative side. Yeah, now this means that the hyperbola consists of two parts called its branches, going left and the other one going right. And when we draw a hyperbola, it is useful to first draw its asymptote lines, which are the dashed lines y equals b over a times x and y equals negative b over ax, as derived in my earlier video or videos on both the horizontal and vertical hyperbolas on slant asymptotes, and the link will be in the description below. Those were my last two videos that I did, so make sure to watch those to basically see the proof that these are the asymptote lines. So both branches of the hyperbola approach the asymptotes, that is, they come arbitrarily close to the asymptotes, yet never reach them. Thus, to summarize, the hyperbola is given by the formula. Yeah, so I'll write down the formula and basically go over the graph as well with all the terms. So it's given by this formula, x squared over a squared, like this, minus y squared over b squared equals to 1, and where the foci, so I'll write dot here, foci is equal to, well, plus or minus c and 0, like that. That's the foci, or the focus, each one. And then we have the c value is going to be equal to a squared plus b squared. And again, recall from this one, definition of b squared was just scrolling up. B squared is just c squared minus a squared, so we can just move the a on the other side, just becomes the addition of it. So we have b squared equals to c squared minus a squared. Move that over, we just get c squared equals a squared plus b squared. And then the vertices, these are known as vertices, the endpoints or the tips of the hyperbola. These are at plus or minus a, like this, and 0. Like this is assuming it's all on the x-axis for the foci, and the vertices are going to be on it as well if the foci is. So the asymptotes, again, the asymptote lines, asymptotes or slant asymptote lines are y equals to plus or minus b over ax, as shown in my earlier video and written over there, so make sure to watch that. And then if we were to graph all this out, we get like this. Let's graph this out. This is the x, this is the y-axis, so let's just graph out the slant asymptote lines first. Goes across like that and like this, and then this one goes all the way across this part like that. Let's try this better. Actually, here I quickly just drew them with dashed lines. It's a bit easier. So again, it's easier to draw these first. So this is the positive side, y equals b over a times x, and then this side on this one's going to be going the downwards one, y equals negative b over a x, like that. And then this is the origin, and let's draw the vertices is going to be somewhere here. Let's say that's a 0, and then it branches out like this. It gets closer and closer to it, and let's draw this a bit better. Just go something like that, and then this side goes down somewhere like that and approaches those lines. And then let's say the c or the foci is going to be at c 0, the positive side, and then you just mirror everything onto this side. And also, let's say this one here, negative c 0, so negative c 0 like that. And this one is our a0, and then expand this all the way out, but approaching like that. So approaching the asymptotes, but never actually reaching it. And now, similarly, if the foci of a hyperbola are on the y-axis, then by reversing the roles of x and y, we obtain the formula for the hyperbola. Or actually, I'll just like to add vertical hyperbola. So what we end up having is we reverse the x and y's, as explained in my last video on the vertical hyperbola asymptote lines for the slant asymptotes. So we have y squared over a squared, and then we subtract it by x squared over b squared, like that. And this equals to 1. So we switch the x and y's, and then in this case here we're going to have where now the foci are going to be on the on the y-axis, so the x is going to be 0, and then we have this is going to be plus or minus c, and then the vertices, or actually where, I'll just write where c is equal to, c squared is equal to a squared plus b squared, and also the vertices as above. vertices is also going to be on the y-axis. It's going to be 0 and plus or minus a. So the vertices are going to be under this, the one we're, or the first term like that. So this case y. So that's going to be the vertical one, y, and then the other one, if it's under the axis, is going to be the horizontal. If so the first one here where we're subtracting from, from this main term there. So now what we have is the asymptotes, and this one, as explained in my earlier video as well, it's going to be just switched around. So y equals plus or minus a over b x, like that. And this basically has to do with the way that when you solve for y, since the y is under this, it has a underneath it, you're going to have a on top when you move it around, as opposed to this one here, where you have the b on top. So when you move everything around, you're going to multiply everything by b, so the b is going to be on top. And again, make sure to watch my earlier videos on that. And then when you graph this all out in the vertical side, we get like this, x and y. Draw this a bit better, like this. X, y, again, draw the dashed, I'll draw them dashed easier, the asymptote lines like that. Just keep going. This is going to be our y equals to plus, or just regular, a over b x, like that. Let's write the b. And then this side here on the other side, like this. This is the negative side going downwards. And this is our y equals to negative a over b x. Let's write this a bit neater. Y equals negative a over b x. And then this is the a0, a 0a, not a0. This is the vertices, 0a and 0 negative a. And then the foci are in somewhere around here. This is going to be 0 negative c. And somewhere up top here, 0 positive c. And then this curves around somewhere like that and approaches the asymptote lines, and so on, like this. Make it approach it. So, and then this part here approaches, and so on. Just move that term out of there. So it goes somewhere like that. Let's draw this a bit better. Okay, so it goes something like that and keeps going on. So yeah, that is all for today. Let's draw this dashed line better. I'll just fix that up. Yeah, so yeah, that's all for today. Hopefully you learned from this pretty extensive definition and derivation video on hyperbolas, as well as briefly on the vertical hyperbola. So when I just mentioned hyperbola like that, usually just mean the horizontal one, but again, depends on the case. And yeah, that's all for today. Hopefully you follow along. It's a pretty extensive video. Hopefully you were able to learn from it and follow it along indeed. Anyways, let me know what you think. Anyways, that's all for today. Thanks for watching. And like always, you can download these exact notes in the link below in the description, as well as viewing these notes on Steemit. Follow me at MES. Link will also be in the description below for this video, for the video notes of this one. Also make sure to check out my private Discord chat room, as well as my cool math forums to post any cool math or science related stuff on there, and also privately or on public forums there. And it was all for today. Thanks for watching, and stay tuned for another Math Easy solution.